So in this segment on gases, we're going to take a look at the kinetic molecular theory of gases, which sounds kind of big and daunting, but if you remember that kinetic just means movement and molecular just molecules. So all we're going to do is just try to explain the properties of gases by looking at the movement of the particles or the molecules. So first we have a few assumptions or postulates related to the kinetic molecular theory. And these can be found in your book on page 20, that's Brown-LeMay, 10th edition. And so the first one is that gases are composed of large number of particles that behave like hard spherical objects in a state of constant random motion. This is also called Brownian motion. Right? Obviously, the atoms aren't large, hard, or are not hard particles, spherical objects, but we're going to make that assumption. Second one is that these particles move in a straight line until they collide with another particle or walls of the container. Actually, I have to take that back. That is actually the Brownian motion. The particles are much smaller than the distance between the individual particles. So that means that when you look at a sample of gas, it's really mostly empty space. There's not a whole lot of matter in there. Next, that the force of attraction between gas particles or between the particles in the walls of the container is insignificant. Particles are moving very quickly. There's so much space between them that there's really no attraction or repulsion that's going to happen there. Next, that the collision between the gas particles or the collision between the walls of the container are perfectly elastic. So there's no energy lost when particles collide with themselves or with the walls of the container. And finally, that the average kinetic energy of a collection of gas particles depends on the temperature of the gas and nothing else. So that tells you that when you have two gases at the same temperature, they would then have the same average kinetic energy. Here we have a kinetic energy distribution curve, and this is something that oftentimes confuses students. The vertical column, the x or vertical axis, the x or y axis, is the fraction of molecules that have a particular root mean squared velocity. That's what this u is. It's the root mean squared velocity. And if we look at different temperatures, the value of that root mean squared velocity would increase as the temperature increases. But the molecules in general would have a whole distribution of different speeds. Obviously, at the higher temperature, there would be a greater number of particles at the higher speed. So you can see that with the red line where it shifts over to the right, indicating that there are more particles that are moving faster at the higher temperature. Notice that the curve also comes down because the total number of particles, which is represented by the area underneath the curve, has to stay constant. So if the curve is shifting over to the right, it's also going to have to come down. So you get a greater distribution of different energies as well. And over here, the E here, we can really just make it a little simpler for ourselves and say that's the kinetic energy. We're not really going to worry too much about what the root mean squared velocity is. It becomes much more significant when you start looking at the more of the physics behind the movement of gases. But we'll probably use mostly just the velocity. So in trying to explain some of our gas laws using the kinetic molecular theory, the postulates there, one of the things that kind of stands out to us is that kinetic energy is proportional to temperature. Okay. So as kinetic energy increases, so does temperature. So we can kind of get that understanding that as the particles move faster, the temperature goes up. Or conversely, if our temperature goes up, we know that the particles are moving faster. Well, if we combine this with our idea of pressure being equal to force divided by the area over which that force is exerted, we can factor in some more reasoning skills to explain the gas laws. So if we're going to take a look at things that affect the pressure, we can look at the force and say, well, the force is going to be proportional to the number of molecules that are hitting. So we're talking about the pressure on the outside of the container, the walls of the container. That force is going to be proportional to how many molecules are hitting the container. The more molecules that hit the container, the larger the force is going to be. That force is also going to be proportional to the number of times that those particles hit, or the force with which they hit, which is going to be proportional to the kinetic energy, which we just said is proportional to the temperature. So we know that the force will increase due to that increase in temperature, because those particles are going to hit more often, and they'll hit with more force. And finally, if we take a look at the area, well, we know that area is going to increase with the area of the container. The surface area of the container will increase as the volume increases. So area is going to be proportional to the volume that contains that gas. So we can see that our, in our PV equals nRT, so our relationship there, we have all these things covered. There's the pressure, the number of moles, the temperature, and the volume. So we can use these different relationships then to explain any of our gas laws and how those gas particles behave. So it's one of the things that we'll do in class, or we'll have you practice on your own, is to how to explain those different relationships using these proportionalities.